Hello, it's me, and I have a question that was posed to me by a viewer regarding this parity situation on the Professor Pyraminx. So I had to pull the Professor Pyraminx off the shelf and see what we can do with this. So this is a situation where you see that one side is completely solved, and I tried to get this to exactly the situation that the particular viewer was describing, and I think I did. You can see that the green center is within the red center is within the blue center is within the green. So basically what happened is that the technique that was used with this was a reduction technique where they took the Professor Pyraminx and they tried to reduce it to this guy, a Jing's Pyraminx, and then solve it as such, which you could do. Basically, if you look at this like a Jing's Pyraminx, these two correlate over here. This doesn't really participate much in the scramble or in the solve, so really this and this correlate. In terms of edges, you've got this, all of these get reduced to this, and then you've got the center, which is all of these get reduced to this. So why not? You can look at it like that. Now it's interesting because this is really kind of a two-layer puzzle, I guess. And this is a 1, 2, 3, 4-layer puzzle over here. The other thing, the other Pyraminx that's like this is the Master Pyraminx. Now with the Master Pyraminx, this is actually the next step up from a Master Pyraminx, but you can also think of it as somewhat of a step up from the Jing's Pyraminx as well. You can look at this the same way. In other words, this correlates with this corner over here. This is an edge, but instead there's 3. And then you have a center that's over here, and it's just one center. So basically, you have a reduction potentially of the edges here to match with this, but you don't have any reduction of the center because you just have one center. Jing's Pyraminx is more of a skewb kind of a concept. How the Pyraminx works is the Pyraminx looks like this, only it has no center. It's all just edges and corners. So it's a little confusing, but basically what happens is that whether you're reducing this guy to this or this guy to this, either by bringing the corners down, you can look at both of these as variable reductions into a Jing's Pyraminx. In this case, you don't have to reduce the center, you just reduce the edges to here. In this case, you reduce everything. But that brings into mind the concept of parity, because when you're taking a more complicated puzzle like this in a scrambled state and you're reducing it to a puzzle like this, there is the possibility, because you have more degrees of freedom and more motions that you can use as you tear into the center over here, there is the possibility of putting it into a state after you've reduced it into the Jing's Pyraminx state that it could never have been scrambled to had you started off with a Jing's Pyraminx state. In essence, that really is parity, or the parity of reduction. Parity of reduction of corners and centers. Because as you're doing that, you're able to put it into almost any conformation that it could possibly go in, but in here you can't. In terms of putting the centers in, there is the algorithm to move the centers around. So you think, well, why don't I just use that? And that's going to be the algorithm where I do, say this is R and this is U. Then I go R, U, R, I, U, I. Then I do it 2 more times. R, U, R, I, U, I, R, U, R, I, U, I. And that does flip these around, but what happened is that these two flipped, the front and the bottom, and these two flipped, the right and the left. So you're always going to have all of them out, either all of them in or all of them out. We can do the same thing over here too. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. So same concept here, and you see that these are out. Now understand, when I did this, there are certain rules that I applied, certain permutations that I could use. Odd number permutations, even number permutations. It doesn't matter, it caused the same pattern between both puzzles. And these permutations that I was restricted by with this puzzle dictated that there's only one state, or only certain fixed states that this could be in. The problem with a more complicated puzzle, when I reduced it into a conformation that the specific permutations held by the rules of the reduced puzzle wouldn't ever be able to hold to. So I defined this as now one of these guys, but I reduced it in a pattern that broke the parity, broke the ability of the permutations of these puzzles to ever be in, which means you can't solve it that way. Both of these I can. So in other words, you have to have all 4 out. So we'll get this back. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, no problems, and we're safe and secure within the confines of the parity of this puzzle because the permutations that we did not break any laws of parity because we didn't pluck any piece out and put them in an impossible situation. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. But we are not so secure in this situation because now I know that no matter what I do, I'm not going to be able to get them in by that. I broke the rules of parity by putting this in a reductive state that the regular permutations would never have been able to scramble it in. So these two can swap and these two can swap, which means green will be in, but the rest will be out. So what do? Well, the way that you deal with any parity, should you have gotten it, is to recognize that you got that parity because you put in areas that don't really belong. And you did that by kind of dissecting into the areas that you reduced. Because the assumption here is that once I've reduced things, once I've put corners in and centers in, I am now not going to touch those. I'm now going to treat them just like the reduced puzzle. I would no sooner do this move than I could do, say, this move here by dissecting through here. And I would no sooner do this move than, say, split this center down here. I have now limited myself to not doing movements like that, but I can't limit myself with that because I put it in incorrectly. I had no way of knowing that at the time. So what I need to do to get this back is I need to actually break my rules and dip into the areas that cause the parity to begin with. This is the archetypic example here. You see with the 4x4, if you just concentrate on the edges here, you'll see 3 are in and 1 are out. This cannot be done on a 3x3 if you follow the specific permutations that are allowed within that. A permutation is a combination of movements. And that permutation is basically what defines the parity, which means what's allowed and what's not allowed. Well, this would not be allowed in a 3x3, but can happen with a 4x4 because in a 4x4 you can dissect into these edges that you reduce down and set I'm not going to touch. I'm going to treat it just like a 3x3. But because we started with an even puzzle, you reduced it in a conformation that could never be scrambled by a 3x3. So, to fix such a parity situation, we have to actually break our rules and dive into this reduced corner and do it right. In this case, it would be the Red Bull algorithm. So the way to fix this, and anytime you have to fix a parity situation, is you have to get out of your reduced state and then find some combinations of moves to quickly and efficiently bring you back. In this case, the Red Bull algorithm. So I have to split it down here to R, to B, to U, L, to up, RI, to up, R, to up, to F, R, to F, LI, to B, to R. And then we got it in here. We've got a situation over here, but I got an algorithm for that too, to flip these two. Is this parity? Yeah, this is also parity because I don't believe that a 3x3 could be in this situation either. So once again, I have to dissect through these reduced areas and no longer call them reduced, go from odd strategy to even strategy to get the right strategy. To U, to R, to F, to U, to U, to F, to R, to U, and what you have is a successful strategy to get out of parity. So, what about this guy? How am I going to get out of this? Do I have a quick and easy algorithm to get through this? And the answer is, sorry to say, I don't. But what I can do to guide you through this is strategy. The best medicine is preventative, which means prevent the situation from happening. If you look at the tutorial that I have on the Professor Pyraminx, one of the first things that I indicate and say is to not land in this situation. And the way to not land in this situation, the way that I do it, is I don't like to do necessarily a reduction method with this, because you can possibly land into this situation. What I like to do is, as I'm defining sides, I put these centers in first, because what I then do after that is, as I load these in one by one by one by one, these centers never change in conformation with each other, in configuration with each other. So The first thing I would do is look back at the previous tutorial that I had with this and see what I did, which was basically as I'm putting in and defining these guys over here, defining my sides, I'm keeping the center there and I'm making sure that they're in place before I move on. And then I slowly put these in. First I put these inner edges that articulate with the center, then I put in these outer edges that where the base is on the outside, then I put these guys in, and then it's solved. And then I slowly put these in using a 5-cycle algorithm that moves these in. So as painstaking as it might seem to put the centers in the way that I do it afterwards, it will always prevent this. The centers here will always be the same, and that algorithm, which is actually the same algorithm that I just showed, moving the centers around, when applied to here, see, if I wanted to move these centers on block, I do the same algorithm, but this would be R here, and this would be U over here. But if I make this R and this U, that's going to variably move these little guys around. This to here, this to here, this to here, this to here, and this to here, already previously demonstrated. Now, what I could do is I could slowly design the shortest number of moves to get this back in, write it down, call it an algorithm, and say there's your algorithm. I'm really not going to do that. I'm just going to kind of go through the strategy of how to get past something like this. Here's what we're going to do. Now, in the strategy that I'm going to have with this, I've tried to minimize motions as much as possible, but really what I'm doing is I'm just kind of diving into first what I thought I had reduced. So I have to dive into the reduction of my edges and even my center. But what I want you to do is I want you to take the slice that contains your center, and I just want you to move it right where it's supposed to be. So in this case, I moved it in a counterclockwise rotation so that the green center is here, blue center is here, red center is here. Now once I've done that, I've taken out these corners and I have to replace these edges rather, and I have to put them in one by one. But I have a little bit of an advantage here because I have a 3-cycle potential here. 1, 2, 3. So here's what I want you to do next with this. Now, if you can kind of plan out what I'm trying to do, this has to make it to here, but I need to exchange it with these guys over here, which means I need to do some deconstruction and reconstruction. The thing about an algorithm is you can deconstruct the puzzle any way you want, do your algorithm, which has just localized changes of specific pieces, and then reconstruct it by reversing what you did into a kind of like an Uber algorithm. So here's what I want you to do. I want you to take the puzzle. Now we're actually going to be doing this motion, but I want to keep our perspective like this. So instead of turning it like this, we're going to do the same motion but relative back to here. So we're actually going to take this part and turn this down like so. Alright, so just to rehash exactly what I'm doing, starting off with this, and I just happen to have the green and blue in front of me, the way to get through this is slice the middle slice here, the one with the middle portion of the edge, in a counterclockwise way. Then I'm going to take my back layers here, keeping this front layer here, and turn it down here in a, I guess what you'd call a B move, which would be a counterclockwise from this standpoint. So just move it down like this. And then what I'm going to do is I'm going to take the bottom portion here and do a D. So I'm just going to move this over here. The reason that I did that is now I've put these three in conjunction to do a nice little 3-cycle pattern. Because now this is going to move to here, then I'm going to move this up in order to get things in. So now what I'm going to do is I'm going to take this middle back here, this middle slice that I did, and I'm going to turn it to a clockwise rotation. So go over here. Then take the same slice and move it up, and then reverse it by moving back and down. Now what I'm immediately going to do is reverse what I did originally and take this bottom portion here, or this down portion here, turn this back like so, and then I'm going to take this layer and turn it back like so. So what did I do? Well, what I did is I placed my centers, and I also placed these edges here. Now, as you recall, there's 2 species of edges, ones that articulate with the center and ones where the bases articulate on the outside. So basically these were put back in, and this was the harder part. These weren't touched, and all I have left are now these guys to do a 3-cycle. This part is pretty intuitive, fairly easy. Basically, you're going to be doing this maneuver and this maneuver. And as long as you're doing that, you're not going to offset what you did with the center. Now, you can just go back to the original tutorial and take it from here, but just by way of minimizing motions, here's what I would do. Take it now and turn it over here so that you have these three within the same plane. What I want to do is I want to do a 3 cycle where I have 2 in one and 1 in another. So I'm going to solve one whole edge here, and again, it might as well be this guy up here. So what I have to do is I'm going to turn, I want this to come up to here, but I'm going to move this down to do it. So let's turn this bottom one out of the way. So I guess if you want to call it a counterclockwise rotation here, I'm going to move this down and then move this across so that this matches up and move it up. This whole side is solved, and now I have 2 that are out over here. What I'm now going to do is turn the puzzle again over here, and now I'm just going to 3 cycle these guys. This belongs up here. It'll find a nice happy home, and this belongs down here, and this belongs, yeah, this belongs down here, and this belongs over here. So the way that I do that 3 cycle here is this will come up to be where it needs to be here. I'll turn this like so, and move it down, and then turn it back. And lo and behold, this is good and this is good. So now we've fairly simply put back everything that we needed to put back, and now the centers. Now as you recall, the algorithm with this is it's the same algorithm that I used to move these centers around. But instead of moving this as my R and this is my U, I'm moving this as my R and this is my U. And the pattern of movement of my centers will be this piece will move here, this piece will move here, this piece will move here, and this piece will move here, and this piece will move here. Impossibly complicated? Not really. But my first step in the process is I want to get one solid bar on each layer. So let's see if I can do one algorithm to get one solid bar on each layer, but I don't want any one side to be solved, or else I'm stuck with right where I started from. So if I hold it here, this green, and I want to hold it to where maybe the one on the bottom has a color that'll come into here. So this green will come here, so I'll be set for that, sort of. This yellow, I don't want this yellow to come here, so what I'm going to do is I'm just going to turn this like so that this blue can harmlessly come here, this blue will harmlessly come here, this blue will be lopped down to here. But I don't want to destroy this, so I'm going to do my second move of deconstruction like this. So now it'll bump this red out and put it to here. So I'll have this whole side in and one over to here. Now if you start to worry about, am I going to remember what I did? Well, I have this yellow area here. If I just remember to move it back to here, then it's going to fall into place. So it shouldn't be too hard. So we do the algorithm, R, U, RI, UI, that's 1, 2, 2, 2, 2, 3, 3, 3, 3. Okay, so it did what I wanted, have this whole bar in. Let's go ahead and reconstruct it back. This turns back here, this turns back here. Now I need to put the other green one in, which would seem to come from this one over here. So that's what I'm going to do in terms of deconstruction. I'm going to turn this over here, so that now this green will come here, creating a bar. This yellow, well, I don't want it to be here, because it'll bat this out. So I'm just going to turn this down to here, so that this yellow will come here, this blue will come here, this green. Well, I don't want it to come here, so I'm going to do my last of the deconstruction. I'm just going to remember that I'm moving red away from red. So just move this over here. Well, so this red has to come back to here, and then this will come here. So I'll have all in but one. I'll have all my bars in, rather. So 1, 1. Okay, so from here, let's see what makes sense. This red can come down to here, and this can come over to here. Okay, so now we have what we wanted. All of these bars are in, we just have to move these guys here. So which positioning can be used? One of them has to make sense. Yeah, this blue can come here, this yellow can come here, green here, red here. So this will be endgame here. I'm going to have to turn this over here, so this blue can come over here. This yellow can come over to here, but I don't want to knock this one out, so I'm just going to turn this up like so. So this will come here, this will come here, and this green needs to come over to here. So the last turn that I'm going to do is move this like this. So what I have to remember is that this has to move across like this, which will create a nice red slice. So we'll go ahead and do it. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. So all of our centers are in. Actually, I just remember to go like this to create this red slice, and then bring this up here and bring this across here. So now it's solved. All right, so basically my suggestion, avoid that possibility, avoid that trap as much as you can. But if you do walk into that, I try to minimize the motions as much as possible. Just remember that what to do early on, moving this slice over here, this down, this across, do your 3-cycle exchange, and then quickly move it back. And then do your easy 3-cycle exchange over here, and then all you have to do is just line up these little ones in the center, and I gave you an example of how to do that. So I hope that helped. Thanks for watching.